Son las 10, ¿no?
Está en Teams, entraron en Teams. Hay 9 personas en 9 que están en Teams. En YouTube y Facebook, ¿hizo eso todo? Estoy con el cuadro de... Y de que puedan hacer comunicar. Porque es que si están controlando la máquina. Es otro edificio. Si alguien está haciendo una... Nosotros tenemos que monitorear. Allá todo lo que hacen es monitorear de todo lo que hacen. No hay apoyo de la otra parte, todo que asegura que hay la proyección de todo. Debería ser aquí en chat. El chat, si quieren levantar la mano, podemos también dar el micrófono ahí. No, pero ya yo no me estoy yo creo que sí, yo creo que necesitamos de ver lo que yo pregunté a Alejandro. Tú puedes desbloquear el micrófono de algo y es todo son gracias. Si yo hablo, si la presentación es la de Miguel.
Bueno.
La primera.
Ya está.
Hola, buenos días. Ya tienes eso. Perfecto. Esperamos un par de minutos, ¿no? Sí, yo creo que sí. Yo creo que me escuchan. Entonces vamos a empezar. Sí, me escuchan bien, ¿no? Si tú pones tu audio para ver si funciona. Sí, se escucha. Perfecto. Entonces, bienvenidos a esta 7ª edición de la Escuela de Superconductividad. Es un formato híbrido. Entonces, tenemos hoy 3 charlas. La primera va a ser por el doctor Miguel Lindero Hernández. Es presencial, pero también va a ser proyectada en línea. Después vamos a tener una presentación del doctor Gabriel dos Santos de Brasil. Eso va a ser puramente virtual. Y después, para concluir, vamos a tener una tercera presentación, que es la presentación de Ciro Carsolaio del Instituto Paul Scherrer en Suiza. Con esos 3 expositores vamos a un poco hablar de lo que son las aplicaciones de la superconductividad. Van a haber algunos temas de modelado con el doctor Miguel Lindero Hernández y el doctor Gabriel dos Santos. Después van a ver realmente qué se hacemos con esos modelos con el doctor Ciro Carsolaio. No vamos a perder más tiempo, tenemos 1 hora por cada ponencia y 45 minutos de presentación y dejamos 15 minutos de pregunta. Vamos a hacer una pequeña pausa entre cada presentación para descansar. Y empezamos entonces con el doctor Miguel Lindero Hernández. Yo voy a presentarlo. Obtuvo su doctorado en el Instituto Politécnico Nacional, desarrollando el tema de diseños de bobinas toroidales desmontables para aplicaciones en máquinas de tipo tokamak de fusión nuclear en el 2022. Su experiencia abarca la implementación de módulos termoeléctricos y de diseño de bobinas desmontables para altas corrientes. Es hoy en día un postdoc que está trabajando con su servidor, el doctor Frédéric Trio. Y ¿qué hacemos juntos? Es que hablamos de todo lo que son las aplicaciones de los superconductores en sistemas de grandes escalas, sistemas hechos de superconductores de alta temperatura crítica. Olvidé de mencionar que estamos en el Instituto de Ingeniería, es la segunda parte de esta escuela de superconductividad, se inició en Puebla hace una semana, la próxima semana va a seguir el Instituto de Física de la UNAM, entonces también es un formato presencial y en este caso pueden también conectarse en la red para aprovechar de las charlas, ponencias que van a haber la próxima semana, además de esta semana. Esta semana estamos en el Instituto de Ingeniería en el Salón Rosenbluff y esperamos que van a disfrutar de esta experiencia. Muchas gracias. Por favor, doctor Miguel Lindero.
Buenos días a todos los que están presentes y a los que nos están siguiendo vía remoto. Bueno, el interés del ciclo de histéresis aquí pues radica en estudiar los superconductores en diferentes formulaciones y para ponernos un poquito en contexto, estudiar la interacción entre cintas superconductoras y materiales ferromagnéticos en bobinas de tipo pancake, utilizando diferentes formulaciones electromagnéticas. Básicamente las formulaciones electromagnéticas aquí se utilizan para reducir los tiempos de cómputo. Hay una en específico, una formulación que se utiliza en demasía y que es la formulación H. Ahorita vamos a hablar de la formulación H, de la formulación TA y una formulación relativamente reciente que es la HA. Bien, este es el contenido. Nos ubicamos primeramente en un ciclo de histéresis ordinario, cómo se forma un ciclo de histéresis ordinario cuando nosotros implementamos un campo magnético variable. Posteriormente nos enfocamos en la caracterización de una cinta superconductora, que es el punto de partida para analizar la interacción de los superconductores con los materiales ferromagnéticos. Posteriormente el comportamiento de los superconductores de tipo 2, para pasar después a las bobinas de tipo pancake, cómo están constituidas. Después las aplicaciones de este tipo de bobinas pancake calls, aplicaciones en interactuando estas bobinas con núcleos ferromagnéticos y en algunos casos sin núcleo ferromagnético. Obviamente la implementación de la formulación TA y la HA, la formulación TA ha sido utilizada desde 2016, la HA es relativamente reciente, en algunos pocos años se empezó a utilizar, pero ahorita nos ocupa implementarla porque pues, puede reducir los tiempos de cómputo que si utilizáramos la formulación H. Y finalmente, pues, estas dos formulaciones aplicadas en bobinas de tipo pancake. El ciclo de histéresis básicamente consiste en la magnetización de una muestra de material ferromagnético, aplicamos una intensidad de campo magnético y notamos que si la muestra es virgen, es decir, no tiene los dipolos magnéticos están orientados de manera caótica o azarosa, entonces no tiene un campo magnético o una magnetización resultante. Empezamos en cero, vamos siguiendo la línea punteada. Al momento de aplicar esa intensidad de campo magnético, llegamos al punto A, donde se llega a la saturación. Podemos revertir ese campo, ¿sí? O disminuirlo hasta cero. Llegamos entonces a un estado de retentividad, que es el punto B. Y si invertimos el campo en sentido negativo, la intensidad de campo, que es el eje X, vamos a llegar a un punto C, que es se le llama coercitividad. Seguimos incrementando ese valor, vamos a llegar a un punto opuesto de saturación, al punto del cuadrante número 1, estamos en el cuadrante número 3, y posteriormente pasamos otra vez a cero, teniendo una magnetización ahí remanente en la muestra. Para regresar y cerrar el ciclo, aplicamos otra vez una intensidad de campo magnético positiva para llegar otra vez al punto donde partimos. Y así sucesivamente, si estamos aplicando constantemente esta intensidad de campo magnético, vamos a replicar este ciclo. Básicamente este ciclo lo que nos va a decir pues es la energía implementada para la magnetización. El área dentro de este ciclo es lo que nos dice. Las caracterizaciones típicas de las cintas superconductoras nos compete porque hay un parámetro importante que se llama la corriente crítica. La corriente crítica pues es digamos que es la corriente que el material o la cinta puede conducir, ¿sí?, antes de llegar a un estado no superconductor. Digamos que es el parámetro límite en el cual nosotros podemos utilizar la cinta superconductora. Aquí tenemos una cinta superconductora que está compuesta por materiales, un stack o sándwich de materiales típicos como cobre y plata. Estos básicamente sirven para protegerla cuando la metemos en nitrógeno líquido. En algún momento sobrepasamos la corriente crítica, el material pierde su estado superconductor y la corriente pues empieza a fluir en los otros materiales ordinarios. Aquí tenemos una corriente, una curva típica, voltaje corriente, en donde pues se extrae la corriente crítica a través de la ley de potencia. Aquí tenemos un diagrama esquemático donde metemos la cinta superconductora en un crióstato en el que tiene pues nitrógeno líquido. Tenemos una fuente DC, aquí tenemos dos opciones, pero en este caso utilizamos una fuente DC, aplicamos una diferencia de potencial y hacemos fluir una corriente variable dependiendo del resistor ajustable. Registramos el voltaje, ¿sí?, y podemos también registrar la corriente y registrar nuestra curva, y en este punto pues nosotros podemos extraer la corriente crítica. Es así como se caracteriza una cinta superconductora. Entonces ya más o menos teniendo idea de la caracterización de la cinta superconductora, nosotros podemos ahora analizar el ciclo de histéresis, el comportamiento del ciclo de histéresis en superconductores de tipo 2 sin material ferromagnético. En la figura 5A, nosotros tenemos tres zonas, S1, S2 y N. Aquí en esta zona, cuando nosotros magnetizamos una muestra de material superconductor, se dice que la zona 1 corresponde al efecto Meissner, donde todo el campo magnético que aplicamos a la muestra, la muestra lo repele. No hay campo magnético dentro de la muestra. En la zona S2, que es una zona mixta, con un intervalo de campo crítico 1 y campo crítico 2. En esta zona, parcialmente las líneas de flujo magnético en la muestra pueden ingresar, y típicamente en esta zona es donde pues existen la mayoría de aplicaciones, una zona mixta. Pasando de esta zona S2, ¿sí?, llegamos a una zona donde pues deja de existir la superconductividad, es una zona ordinaria, zona normal, excedemos la corriente crítica, ¿sí?, y ahí pues no nos interesa trabajar el material, ¿verdad? Aquí pues obviamente tenemos un ciclo de histéresis típico en un material superconductor, donde tenemos la zona 1, ¿sí?, la zona 2. En la zona 2 pues nosotros podemos ver la curva de magnetización con respecto a la aplicación de la intensidad de campo magnético, como se vio en el ciclo de histéresis ordinario, ¿sí? Vamos recorriendo este ciclo a medida que la intensidad de campo magnético es cambiante. Ajá. Una pancake coil pues es un arrollamiento de cintas superconductoras, ¿sí?, en donde pues para su análisis lo que nos interesa de este arreglo pues es cuantificar cuánta corriente puede conducir, cuánta densidad de corriente se le puede aplicar a este material superconductor, y específicamente cuánta densidad de flujo magnético nos puede dar. Típicamente pues para las pancake coils en el centro. Para ello pues modelamos las pancake coils en un software llamado COMSOL. Hacemos un modelo, ¿sí?, posteriormente lo mallamos, hacemos un mallado, establecemos la formulación, hay diferentes tipos de formulaciones, elegimos típicamente la formulación H para comparar las demás formulaciones en tiempos de cómputo. La formulación H es la más utilizada, sin embargo, gasta mucho tiempo en ser resuelta. Los dos parámetros que nos interesan pues es la densidad de corriente normalizada en el stack y la densidad de flujo magnético, ¿sí? Son esos dos parámetros que nos interesan. Aquí pues esta pancake coils no tiene, como vemos, no tiene un ferromagnético, ¿sí? Las aplicaciones, bueno, los colegas aquí en el instituto, el colega Berrospe, pues ha implementado la formulación TA para efectivamente estudiar el campo magnético en el centro, ¿sí?, de una serie de stacks de pancake coils, ¿sí? Aquí tenemos varios stacks de pancake, son los rectángulos, ¿sí? Básicamente nos interesa medir la intensidad de campo magnético en el centro y el ciclo de histéresis debido a las screening currents o corrientes de apantallamiento. Aquí este es un solenoide que se utiliza en fusión nuclear para generar 32 teslas, ¿sí? Aquí lo que se hace pues se utiliza la ley de potencia, se utiliza la fórmula de Kim. La fórmula de Kim pues describe básicamente la densidad de corriente crítica en función de los campos magnéticos radiales y en Z, que serían los campos de interés en un modelo axisimétrico de este tipo. En la formulación TA las cintas típicamente son de una dimensión, todo este stack de cintas, ¿sí?, las hacemos un bulto, la formulación T se aplica a las cintas, mientras que la formulación A se aplica a todo el espacio que rodea a las cintas. Hacemos aquí, para cargar el solenoide, aplicamos una corriente triangular, ¿sí? Gradualmente vamos aplicando la corriente, ¿sí?, cíclicamente. Es parecida a una senoidal, nada más que obviamente los cambios son súbitos, discontinuos en estos puntos, y se pueden cuantificar lo que se llaman pérdidas, que al final de cuentas es lo que interesa en el análisis, ¿sí? Entonces, esta formulación TA se ha notado que ahorra tiempos de cómputo, relativamente sencilla de implementar, con este par de ecuaciones, en donde pues A es el vector potencial magnético y J es la corriente que se establece de forma perpendicular a la página en cada una de las cintas. Con estas dos ecuaciones se meten en COMSOL y se obtiene el análisis el solenoide. Ajá. En este solenoide, aquí lo que el colega en estas aplicaciones ha obtenido, pues básicamente es una cuantificación de el campo inducido debido a las corrientes de apantallamiento que suceden en los superconductores. Básicamente es un ciclo, ¿sí? Un ciclo que nos va a decir, nos dice qué tanto se disminuye el campo, la intensidad de campo magnético aquí, comparado con un modelo de un solenoide hecho con materiales normales. Un campo magnético nominal se mide en un solenoide que es, digamos, un solenoide hipotético que se construye con alambre ordinario, ¿sí? Ahí no van a suceder histéresis de este tipo, no van a suceder ciclos, y básicamente cuando utilizamos, en vez de materiales normales, utilizamos materiales superconductores, se da este ciclo que lo que hace es disminuir la intensidad de campo magnético en el centro. Ajá. Otras aplicaciones interesantes en donde sí, efectivamente ya aquí meten los materiales ferromagnéticos, es en la transferencia inalámbrica de energía para, que esto hoy en día pues está muy de moda, es la transferencia de energía inalámbrica entre dos bobinas, una superconductora, que es la que va a transferir, es el emisor, y una que va a recibir, que sería la bobina hecha de material ordinario. Ajá. Entonces aquí pues obviamente ya entra en juego la aplicación de la formulación TA y HA para analizar la interacción que tiene el material ferromagnético y las cintas superconductoras. Aquí se han hecho estudios en donde el material ferromagnético incrementa el acoplamiento y hace que haya una mayor eficiencia en la transferencia de la energía inalámbrica. Ajá. Rápidamente nada más, las fuentes para alimentar estas pancake calls a diferentes frecuencias, pues básicamente son circuitos puente, ajá, donde pues se pueden alcanzar frecuencias de 400 kilohertz, desde 100 hasta 400 kilohertz, con pulsos de ancho modulado, PWM, de 100 kilohertz con ciclos de trabajo de 0.5. Estas fuentes para alimentar esas bobinas las podemos escalar en potencia, haciendo, pues, replicando ese circuito y poniendo más cantidad de MOSFETs, y donde aquí pues vamos a tener el circuito resonador o circuito tanque. Esta va a ser la bobina superconductora con un capacitor, un resistor, y pues vamos a coordinar el switcheo para que pues podamos nosotros generar estos valores de voltaje en la bobina. Ajá. Básicamente necesitamos cuantificar la corriente crítica, tenemos el Hall bridge, tenemos nuestro circuito, nuestro banco de capacitores con nuestra bobina. Ajá. Lo que aquí necesitamos hacer pues es hacer los registros de la corriente eléctrica que se puede generar. que a final de cuentas se puede traducir en campo magnético. Entonces aquí es interesante, este estudio no se ha hecho, es una idea que sale, en donde pues implementar la formulación HA y la TA para cuantificar esas transferencias. Esta sería otra aplicación. Otra de las aplicaciones que nos compete y nos interesa hoy en día pues son los transformadores superconductores, donde estos transformadores obviamente contienen materiales ferromagnéticos y cintas superconductoras, ¿verdad? Entonces, aquí un poquito de teoría en cuanto a la formulación H, la TA y la HA. Necesitamos validar la formulación. Si queremos implementar una nueva formulación, necesitamos validarla con una que ya se haya usado y una que ya esté validada experimentalmente. Como lo mencionaba al principio, la formulación H es de las formulaciones que más uso han tenido, por lo tanto, pues ha sido la referencia. Posteriormente, pues aparece la formulación TA y la que ahorita nosotros estamos implementando, que es la HA, en donde pues juega un papel importante el ferromagnético y la cinta superconductora. Y vamos a notar que los tiempos de cómputo pues son similares a los de la TA y se podrían reducir ahí con algunas estratagemas que nosotros implementemos. La formulación H, pues básicamente partimos de la ecuación conocida, el rotacional de H es igual a J, después introducimos la ley de Faraday para escribir la ecuación número 2, ¿sí? Acoplando 1 y 2 tenemos esta otra ecuación donde únicamente vemos que ahí aparece H, utilizamos la resistividad también, acoplamos estas ecuaciones en el software console, ¿sí? Y podemos hacer el análisis de H. La formulación, yendo a la formulación TA, necesitamos estas dos ecuaciones. J la podemos escribir en función del potencial vectorial T, B la podemos escribir en función del potencial vectorial A, y estas dos ecuaciones son las que vamos a introducir en COMSOL, transformadas un poquito aquí con la aplicación de Maxwell-Ampere. Obtenemos la ecuación número 7, ¿sí? Combinada con la ecuación de Maxwell-Faraday, tenemos esta otra ecuación, y finalmente pues esas son las que introducimos en COMSOL, con algunas condiciones de frontera. Decíamos que las cintas son unidimensionales, las convertimos en algo que se le conoce como bulto, ¿sí? Y todas estas condiciones las introducimos en COMSOL y tenemos la aplicación de la formulación TA. En cuanto a la formulación H, pues vamos a decir que partimos nuestro universo en dos dominios. El dominio donde están las cintas va a ser, vamos a aplicar ahí la formulación H, y en el dominio restante vamos a aplicar la formulación A. Estas básicamente son este par de ecuaciones las que metemos en COMSOL para hacer el análisis. En cuanto a la validación, pues en términos sencillos, para validar estas tres formulaciones, primeramente tomamos la más utilizada, que es la H. Simplemente agarramos un stack de cintas superconductoras, 10 en este caso, ¿sí? Y lo que hacemos ahí es cuantificar el valor de el coeficiente de determinación en las otras formulaciones. Si el coeficiente de determinación es 0.999, se dice que es un buen criterio para que la validez de la formulación que estamos implementando pues es relativamente alta. Aquí la TA nos dio este valor, mientras que la HA nos dio un valor de 0.9867. Entonces aquí quizá hay que hacerle todavía alguna mejoría para llegar a un valor mucho más grande. Esto es en cuanto a validez. Cuando validamos, pues notamos que la densidad de flujo magnético pues se replica, ¿no? En los tres casos, en la TA y la HA comparadas con la H, que es la más utilizada. Ahora, en cuanto a nuestros estudios, habíamos dicho por qué nos interesa aplicar la HA, pues porque ya estamos implementando las cintas superconductoras con materiales ferromagnéticos. Aquí vemos el material ferromagnético, aquí está nuestro modelo, el stack de las cintas, que forma un solenoide, pero cada una de estos rectangulitos pues, es una pancake coil. Entonces, lo que nos interesa aquí es el ciclo de histéresis debido a las corrientes de apantallamiento que se inducen. Ajá. Entonces, aquí en nuestro estudio, pues básicamente los dos parámetros de interés, la densidad de corriente, que la podemos en algún momento normalizar con respecto a la densidad de corriente crítica, y la densidad de flujo magnético. Ajá. Este es aplicando la formulación TA. Ajá. En esta formulación nosotros vamos a notar aquí en el punto 0, ¿sí? Vamos a notar el ciclo un ciclo de histerético, ¿sí? Un ciclo histerético que tiene esta forma. Esta forma obviamente es diferente al ciclo de histéresis de el colega Berrospe, ajá, debido a que nosotros ya estamos metiendo un material ferromagnético, ajá, estamos metiendo un material ferromagnético y el ciclo de histéresis pues tiene una forma diferente, es lo que nosotros estamos aquí notando, aplicando la formulación TA, ¿sí? Ahora, aplicando la formulación HA, vemos que hay una réplica de densidad de flujo magnético y de densidad de corriente. Ajá. Aplicando la formulación HA, habíamos dicho que encerramos los superconductores en la formulación H y el resto es la formulación A. Entonces aquí obviamente todavía nos falta cuantificar típicamente la duración en tiempo de la simulación TA y la HA, pues no pasa de un par de horas, ¿sí? Más o menos anda muy similar, pero aquí todavía nos falta extraer el ciclo de histéresis que tenemos aquí en la TA. Ajá. Entonces, este trabajo, estos resultados, dan pie al estudio de aplicaciones, ajá, implementando la formulación HA, como lo dije, en transformadores y en transferencia inalámbrica, donde pues juega un papel importante el material ferromagnético y quizá en cables, ¿no? Pero en cables típicamente el núcleo es de un material diamagnético como el aluminio o el cobre. Ajá. Y pues de mi parte sería todo. Si tienen alguna pregunta, pues con gusto podemos tratar de contestarla.
Muchas gracias, doctor Miguel Lindero. Entonces, si hay preguntas por Teams, pueden escribir en el chat o levantar la mano si quieren prender su micrófono. Si no, en YouTube, yo creo que pueden poner un comentario en Facebook también, estamos monitoreando. Tenemos un poco de tiempo, si hay una pregunta, una duda. Sí, aquí presencial.
Hola, ¿me escuchan?
Sí.
¿También allá? ¿Sí? ¿Ya? Ok. Muy interesante la plática, creo que nos da un panorama diferente en el acercamiento a la superconductividad con los campos críticos. Y justo me llama la atención tu figura 5 de la magnetización con el campo crítico, la anterior. Entonces ahí se me hace interesante, por ejemplo, que la magnetización no se hace máxima cuando el campo crítico es 0. ¿Será porque es superconductor tipo 2 o habrá otra influencia al respecto?
Por ser de superconductor tipo 2, bueno, el superconductor tipo 1 realmente no he analizado el ciclo de histéresis, solamente analicé este ciclo de histéresis y efectivamente no es máxima, como tú dices, ¿no? Y ahí no.
Perdón, ¿tendrás alguna idea por qué no es ahí el máximo? Porque digo, en los materiales ferros sí se hace cero cuando es la magnetización máxima, ¿no? Entonces, es curiosidad, porque no había visto yo así, con esta tensión que tienes, esta figura.
Ok, pues sí, necesitaría en principio investigar ahí el indicio, ¿no? ¿Sí? Sí. No, pero está bien, está bien.
Es pura curiosidad, muchas gracias.
Salen preguntas que a veces no podemos contestar en el momento. Gracias.
Muchas gracias. Hay una pregunta en línea del doctor Gabriel dos Santos, de hecho. Yo creo que puedes hablar. You can talk, I think. It should work.
Thank you, thank you. ¿Ustedes me escuchan?
Sí, te escuchamos.
Pronto. Me gustaría saber un poco sobre las aplicaciones de la formulación TA para la transferencia de potencia sin cables. Sin cables. Me interesó bastante, pero una cosa que me quedó un poco curioso es que en esta implementación, ¿usted ha utilizado materiales ferromagnéticos o no? En estas últimas implementaciones que usted ha presentado en tu lámina.
Sí, bueno, los últimos resultados en donde nosotros aplicamos la TA y la HA, estamos metiendo un material ferromagnético. Ajá. En la...
Vale, pero ¿dónde está? Esto que no identifique.
Aquí está.
Yo no estoy viendo, te estaba apuntando. No sé, ¿se puede poner en slide? Porque no estoy viendo dónde está apuntando.
A ver, ¿dónde? Aquí el mouse. Bueno, en la figura 27, ¿puedes ver la figura 27?
Sí, estoy viendo.
Notas el rectángulo, el primer rectángulo de izquierda a derecha.
Sí. Pero esto no es entonces
donde está el eje axisimétrico, el eje vertical de 0. Ajá.
Vale, sí, estoy viendo. Pero ya entendí.
Sí, ese rectangulito es el material ferromagnético. Ahí lo están marcando.
Vale.
Ajá.
Vale, gracias. Ahora entendí. Gracias.
Ajá, y en la HA, pues obviamente también es lo que introducimos y pues vemos la réplica que hay en los resultados de densidad de corriente y densidad de flujo magnético. Son los resultados recientes, ¿no? Faltaría implementarlos en los transformadores y en la transferencia inalámbrica, variando la frecuencia.
Sí, vale.
¿Ok?
Vale. Gracias. Muchas gracias.
De nada.
Gracias. No sé si hay otras preguntas en línea o aquí, presencial. ¿No? ¿Hay en línea? ¿No? ¿En Facebook o en YouTube? ¿No? Si no hay más preguntas, yo tengo una pregunta. En la transferencia inalámbrica, ¿cuál es la frecuencia para transferir la onda electromagnética?
Típicamente para transferir la onda electromagnética a mayor eficiencia y mayor acoplamiento, se ha encontrado que es de 85 kHz, pero hacen pruebas hasta...
85 kilos, eso es para material convencional, ¿no?
¿Material convencional?
Sí, material de cobre, por ejemplo, ¿no?
No, en materiales superconductores
es 85 kHz.
5 kHz.
Para material superconductor.
Materiales superconductores.
En este caso, ¿cuál es el material superconductor que se utiliza?
El REPCO.
¿El REPCO?
Ajá.
Con el típico o hay algo que se tiene que hacer?
Cintas superconductoras típicas,
Ok.
pancake coils, y meten el ferromagnético y se dan cuenta que el acoplamiento entre bobinas, la transferencia, vaya, la eficiencia, se incrementa a que si no lo tuviera.
En comparación de un material convencional, ¿cuál es el ventaja?
La potencia que puedes transmitir y el tiempo en el que puedes transferir esa energía, que es el interés básico en los autos eléctricos ahorita. La rapidez con la que transfieres esa energía. Entonces, de la densidad energética, vaya.
Ok, gracias. ¿No hay más dudas, preguntas? ¿Sí? ¿En línea hay una pregunta? ¿Quién?
Yo tengo una
Doctor
pregunta.
Edgar Berospe. Por favor, Edgar.
Sí,
Adelante.
sí, mi pregunta es, las screening currents producen una desviación del campo magnético deseado, ¿no? Por ejemplo, en las gráficas que viste que pusiste de las bobinas, en el centro de la bobina el ciclo de histéresis genera una desviación en el campo magnético. Eso. Ahí en el centro de la bobina hay una desviación, o sea, se esperan 32, creo, en esa bobina, pero obtienes un poco menos por las corrientes de screening currents. Mi pregunta es, en las aplicaciones o sea, no sé si tú sepas, si esas desviaciones, o sea, ese campo, es importante o impacta en las aplicaciones de fusión, porque en este caso es un imán de uso científico y pues impacta, pero en las aplicaciones de fusión es importante o basta, o sea, o es innecesario hacer estos cálculos para el diseño en aplicaciones de fusión.
Pues en las aplicaciones de fusión sí impacta porque pues tú necesitas conocer el campo exacto, ¿sí? Suponemos que este es un solenoide central para producir la corriente de plasma en un tokamak, ¿sí? Vale. Entonces, sí necesitas establecer el efecto que estas screening currents tienen en ese campo para, pues obviamente, tener una idea del confinamiento magnético y que finalmente va a impactar en las inestabilidades de ese confinamiento.
Sí, seguro, pero por ejemplo, no recuerdo, pero aquí creo que la desviación del campo es como menor al 1%. La verdad es que no recuerdo, pero ¿tendrás una idea
sí, bueno, en tu estudio...
1%, 2%, 10%, ¿qué es aceptable ahí?
Sí, ahí no sabía decir, no he estudiado los solenoides en el tokamak, no sé hasta qué punto influya o en qué porcentaje esté, ¿no?
Vale. Va. Esa era la pregunta. Gracias por la presentación, Miguel.
Ok, gracias.
Gracias. ¿Una pregunta presencial, doctor Miguel Ángel?
¿Ya? Ok. Gracias por tu plática, Miguel. Me llama la atención de que mencionaste varias formulaciones para describir los diferentes superconductores. ¿Cuáles son los pros y los contras de, por ejemplo, la formulación H, la formulación TA, la formulación JA? ¿Por qué usar una o por qué usar otra?
Típicamente en la implementación en COMSOL es el tiempo, ¿no? El parámetro de interés. Cuando pasamos de 2D a 3D, ¿sí? Si utilizamos H, la formulación H funciona en 2D y en 3D, pero en 3D los tiempos de cómputo pueden llegar a semanas o a meses, entonces eso ya es costoso, entonces por ello se busca alternativas como la formulación TA, que pues si la pasas a 3D quizá no sean semanas, sea un día o 12 horas, ¿sí? Es lo que hemos estado viendo. Brincar de 2D a 3D, los tiempos de cómputo se disparan. Ajá.
Sí, pero eso es lo que estamos observando, digamos, que hay ganancia, digamos, en tiempo, pero en el fondo, digamos, ¿qué es lo que estaría haciendo que esta formulación, la TA, por ejemplo, digamos, sea mejor que la H? O sea, porque al final de cuentas estamos resolviendo ecuaciones, diferentes ecuaciones que van a resultar, ¿no? El tipo de ecuaciones, digamos, que están apareciendo se ven muy transformadas como para que al momento de calcularlas, utilizando, pues, claro, los programas de cómputo, bajen, digamos, el tiempo de cómputo. Es nada más el tipo de ecuación, digamos, que estás obteniendo y que estás resolviendo.
No, es el dominio, ¿no? Por ejemplo, las cintas en la TA, el dominio para resolver las ecuaciones en las cintas superconductoras, pues es la implementación del vector T, ¿no? El vector potencial T, ahí en ese dominio, ¿sí? Y fuera de ese dominio, pues es el A, ¿no? Alrededor, o sea, digamos lo que no está resolviendo ecuaciones redundantes.
Ok, gracias.
Gracias. ¿Hay otras preguntas? ¿Sí? Adelante.
¿Qué tal, Miguel?
Hola, hola.
Bueno, una pregunta aquí. ¿Cómo representas tu bobina superconductora? ¿Qué parámetros tomas en cuenta, ¿no?, para representarlo en el circuito eléctrico que has mencionado? Y otra, ¿cuál sería? Porque comentaste que estás en tarea, ¿no?, en desarrollar eso. ¿Cómo, o sea, modelarías aparte? O sea, ¿tomarías la corriente de tu circuito retroalimentando a tu modelo de elementos finitos, o primero modelas tu elemento finito para determinar los parámetros que representen en tu circuito eléctrico? ¿Tienes alguna estrategia?
A ver, no entiendo mucho bien tu pregunta.
Ok. Primero serían cuáles son los parámetros importantes para representar tu bobina superconductora en el circuito eléctrico, ¿no?
Ajá.
Y la otra, ¿qué tomarías primero? Si trabajarías primero como en el elemento finito, en console, tomando, yo me imagino, la corriente y resolver tus parámetros en la bobina superconductora, y después representarlo en tu circuito. ¿Así sería, o cuál sería tu?
Pues primero, en principio, los parámetros eléctricos, pues como la resistencia y la inductancia, pues la podemos, como son parámetros geométricos, pues los podemos estimar y los podemos introducir en console, y de acuerdo al tamaño de la cinta, pues nosotros podemos hacer una búsqueda de las corrientes críticas que puede soportar, ¿no? Y podemos meter esos parámetros en console, modelarlos con su geometría y echarlo a andar con la formulación deseada, ¿no?
Gracias. ¿Hay más preguntas, dudas? No, entonces concluimos agradeciendo de nuevo al doctor Miguel Lindero Hernández por su presentación y su tiempo. Muchas gracias.
Okay. Gracias a todos.
Para concluir, una cosa más, un reconocimiento y un regalito del Instituto de Ingeniería.
Chocolates.
No.
Gracias.
Es una taza. Gracias. Muchas gracias. Entonces son las 10:50. Yo creo que tomamos 10 minutos de descanso, y a las 11 puntual empezamos con el doctor Gabriel Dos Santos para la segunda presentación. Muchas gracias. Nos vemos en 10 minutos.
escucho nada.
No? Hola? Can you hear me, Gabriel? Can you hear me, Gabriel? Hello?
Ahora sí. Ahora estoy
Yes?
escuchando.
Okay.
Gracias.
Excellent. So I was saying, Gabriel, I will introduce you. So you received the PhD in electrical engineering in 2022 at the University Federal Fluminense in Brazil. He currently works as a professor at the State University of Rio de Janeiro and as a postdoctoral researcher at the Federal University of Rio de Janeiro. He worked in the industry as an engineer in the area of electrical studies of power system for high and extra high voltage systems. He worked on steady state, short circuit, transient, electromechanical, electromagnetic analysis studies. He has also served as a product engineer responsible for developing no electrical machines. So welcome, Dr. Gabriel dos Santos, and the floor is yours. Thank you.
Thank you. Let me share my screen. ¿Ustedes pueden ver mi pantalla?
Sí, yes, we can. Please go ahead.
Thank you. Entonces, muchas gracias. Iniciando esta presentación, agradeciendo al profesor Frederick por esta invitación. Para mí es una grande honra participar de este evento. Muchas gracias y espero que en este contenido sea útil para todos ustedes. Bien, hoy voy a hablar de una implementación de una formulación muy reciente, la formulación JA, para simulación de dispositivos superconductores aplicados a esto.
Gabriel,
Bien.
one thing is I saw that you were presenting in English because some colleagues from other countries will probably connect with students. So
Okay,
if you speak Spanish, it's going to be a little bit difficult here. So please, if you can go ahead. Sorry about that.
Okay. No problem. So as I was studying, today I will talk more about the simulation of superconducting device utilizing the very recently JA formulation. So this presentation will cover an introduction very briefly, a methodology that will guide us how to implement and how to model the JA formulation, and some examples of the JA's formulation, presents as well some publications in this topic and the conclusion. Okay, so talk about the warning of the global warming, and we need to find some solutions to avoid these increases of the temperature along the year. Including here in Brazil, we have experienced the most high temperature ever in the several years here, and so it's a real, and we need to care about that. So our way to do that is the energy transition, and this energy transition is about the generation, the transmission, the distribution of the systems, that we need to put it more efficient and renewable. And here we insert the superconducting materials as a solution or potential solution to solve or to help this scenario. Okay, so we need to model some slides, for this kind of applications. For example, we can see some applications here. For example, the superconducting fault colorimeters. Let me get my point here. The transformers, the cables, some superconductor called current emitters, motors and generators, superconducting motor and generators, trains, aviation, superconducting magnetic system, and fusion. All of these systems here we can implement in some parts of this device. We can implement superconducting materials, and of course we have here a range of these superconducting in terms of the magnetic field. We have a range in these magnetic fields, as we can see here. And the question is, how can we solve or how can we implement this kind of superconducting materials? As it has a very non-linear resistivity, it depends on the magnetic field, it depends on the temperature, and it depends on the current that we apply. So the question is, how can we work with these materials, or how can we model these materials as our several nonlinearities and dependence? So we have a solution here to apply solve this problem using the finite difference method or moment method or finite difference methods or so on. It means the numerical methods that we can use to solve this problem and to design this kind of equipment. So applying this kind of equipment is needed to simulate it in some formulations, or it means, as the last presentations told us, that we need to solve, for example, the AV formulation, the H formulation. We can use the HV formulation, HA formulation, and so on. Here in this presentation, I will focus on the JA formulation, very recent formulation that was developed. So here we are in the JA formulation. The JA formulation was proposed by me, by Professor Barbara, that works with me in the same university, by Professor Felipe Sais, Professor Flávio Martins, Guilherme Sotelo, and Rubens Andrade Jr. In this formulation, we look at a system that is a low frequency, and we solve a partial difference equation and an ordinary differential equation. Both these equations we can solve separately. It is important in 5 we solve this separated. It's not a same system. It's a two system equations that we need to solve simultaneously. And so we will solve here the magnetic vector potential, that is the state variable of the H formulation, so the A formulation, that has as a source the current density. And for the J formulation, we have here the current density as a state variable and the magnetic vector potential as a source. And we solve the ordinary difference equation. To characterize the superconducting materials, we use here the power law. There is another forms to characterize the superconductors, but it's more common use the power law, so we use it here. And here we have the critical electrical field that characterize the superconductor, the critical current density, and the current density that passes through for the superconductor, as well as the transition index. For we implement or represent the dependence of this material with the magnetic field and the temperature, we use as well the magnetic field here, the critical current density as a function of magnetic field and the temperature. And we use here the Anderson-Keen law to implement and to use or represent the dependence of the critical current density or the superconducting dependence of the temperature in magnetic field. And what about the coupling between these two formulations? So we use here, we compute here in the J formulation, the current density. And this current density is imposed as a source in the A formulation. and we solve the A formulation and enforce the magnetic vector potential, better speaking, the variation with time of the magnetic vector potential in the JA formulation. And so making this enforcement in these two formulations with coupling them, okay? And so as we know right now how to modeling the JA formulation, we could think how to impose or compute the induced current in some domain of the superconducting, in some superconducting domain. So, for example, if we would like to impose here a current in this domain here, omega ST, imagine that domain is, of course, it's a 2D simulation, and we would like to impose a current in this omega ST domain. How could we do that? So, in this case, we will integrate current density through for this domain and apply an integral restriction here. That means that these integrations minus the current that we would like to imply equal to 0. And so probably we can choose, of course, we can choose in several parts of this implementation. For example, we can choose use or not Lagrange multiplier. It's not needed, but we can choose to help the improvements of this method. But the methodology to implement or to enforce the current is that just to integrate the domain of the integrate the current density in the domain that you would like to implement or to enforce the current minus the current that you would like to imply equal to 0. We will see how to implement it in the console as well. And what about to compute the induced current using this formulation? It's a very, very quickly and very, very easy. We just need to, again, integrate our domain, superconducting domain, that we would like to talk to the software, to the finite element method that this current, the liquid current, will be 0, and so we integrate it and it put it equal to 0, right? Very quickly and very fast. And so if you would like to coupling those domains, for example, if we think that we have right now two superconducting domains, including 2D, and we would like to coupling those domains. How to do that? So we have here omega SC plus and omega SC minus. And I would like to impose a current in omega SC plus. And I would like that the current through all these domains would be minus with the same value but in contrary direction in my omega SC minus. How to do that? Same way, we impose the current in the current density. We impose the current using the methodology that we see in these two last slides, and we use another restriction, integral restriction, that here we can use the current of the superconductor, the integration of the superconductor plus, it means integrating the current in this domain, and we put here minus the plus the omega SC minus, and this integration here will represent this domain here. All of this counts equal to 0. And again, we have here an integral, a restriction that will imply the coupling between these two domains here. Okay. So right now, I would like to show for all of you about some implementations considering bugs and considering thin films superconductors. So in the case of bugs, no change is needed, and the implementation is strictly or straightforward as I showed you up to now. So no chance, no approximation is needed. No approximation is needed here. So I just will modeling my book, modeling my domain of here or other medium that we are inserted here, or probably we could talk here dump hour because probably the superconductor will be in like the nitrogen, and so it's a dump hour, of course. And we apply the same methodology that I told to you up to now. But in the case of superconductive film or ATS tapes, we have several differences between the thickness, between the length, and between the large of this superconductor. And so probably to save the time, it means to avoid a slow computation and to avoid a high computation, we could use an approximation that we call in English a thin strip approximation, or in Spanish, lámina de corriente. So this approximation will just to cover, or just to we change how we coupling those formulations. So in the first time we coupling enforces directly the current density. Right now, to impose this current, to apply this current, we will, firstly, of course, we will approximate the two dimension of the superconductive tape for a thin superconductor. It means in 2D to approximate a domain for a line, and in 3D the book or the block for a surface. So approximating it in the draw, we can apply a boundary condition here, writing by this equation, that is the curve of the normal vector. The curve of the normal vector between the minus or the difference of the magnetic field up and the magnetic field down in this tape here. And doing this approximation, we compute the laminar current, the surface current here, and we can impose it computing the J formulation, the current density, multiply it by the thickness of the superconductor layer, and so we apply it in this boundary condition, right? And so we also can modeling if we have several superconducting tapes as a book, or save the time computation as well. And so to do that, we need to make a correction in the JA formulation that considering these are large domains in the superconducting tape. So we need to make a correction in the superconducting current density, okay, critical current superconducting. So we will apply here. This is scaling that we have the thickness of the superconductor and the thickness of the tape, okay, and making that we can to compute, or we can recalculate the critical current density that we have in the approximation of the superconducting book. Okay. We also have here a multi-scale approximations that we could avoid some calculations in some domains. We can avoid compute the calculation of the current density, and so the non-analyzed superconducting tapes, and we have here as well the analyze of the superconducting tapes. And we, in the non-analyzed superconducting tapes, we made here an approximation. It's a very simple approximation here that we sum the two current densities computed here and divide by 2. Of course, it can be more complex if you have more tapes here, but it's a very directly to implement, I mean. And of course here I also can apply the approximation of the thin film of superconductor as well. And I also would like to emphasize here some open topics, in my opinion, that we could explore in the JA formulations. I could see implementations in the JA formulation books. I could see implementations in the JA formulation in ATS tapes, but not in NGB2 cables. I could not see. So probably it could be very nice to see implementation in this kind of fields as well. It's just a point to remind all of you. And so let's move on right now to developing of the JA formulation. Here I choose the console multiphysics software to implement, but I truly believe that is not just to put in the console multiphysics. We also could have implemented them and another software that we could implement formulations, different equation of formulations as well. So here in console we have to use two models to represent or to modeling the JA formulation. First, the magnetic field and the coefficient form. Here we have boundary if we are applying the thin strip approximation. If not, just coefficient form. So getting here in the electromagnetic fields, we can see the magnetic field model, and coefficient form is in mathematical model, put here in coefficient form PD, or if you are applying the thin strip approximation, we can use here coefficient form boundary PD. Okay. So of course we need to use a time-dependent model as well, because we are coupling. The coupling between those formulations are between a variation of the magnetic field, so with respect to time. So we need to input or need to calculate this variation, so we need to use the time-dependent variation, the time-dependent model. I also would like to emphasize that the JA formulation could to be implemented in PDE or in ODE. There is both ways to implement. So here using inside the console already, we can observe a very, very important approximation that Xi Wang, sorry for my pronunciation, it's a Chinese guy, that briefly and that very early published a very nice article that told us that the discontinuous Lagrange in constant order help us to stabilize the JA formulations better. And so I recommend all of you that would like to use the JA formulation, choose these safe functions. It's what was a very nice discovery and these articles that was published in System. So to implement the JA formulation here, we just use these last terms here, and in the A, I will implement the resistivity of the superconductor, and here I will create the first coupling where the magnetic vector potential in Z direction, that of course we are simulating 2D. We use this first coupling here, that this variable comes from the magnetic vector that comes from the A formulation that is implemented in the magnetic fields here in console. And the external current computed in JA formulation is imposed here as external current density if we are planning to implement a bulk or a bulk approximation. Okay. As I told you, we can impose a current or we can compute a induced current here. For example, if we would like to impose a current, we just apply the integration, that in console there is a way to do that we just call the intop function. That is very nice implemented in console, and integrate the variable here, the current density is U, and minus the applied current that you would like to use. And of course, we don't need to use here equal to 0, because equal to 0 is understandable for console program. Okay, so we don't need to put the equal 0. As well as we would like to compute induced current, we just need to put in a global constraint in top 1 of U. And so here, this in top 1 here is just because I use the first integral. If I would like to change this name, it's completely very, very well done. So comes from here the first example that I would like to present for you in this implementation. We have a very simple example, just to be didactic. We have here the ear and the superconductor domain, where the ear we have the permittivity and the permeability equal to 1. We have here a conductivity equal to 1. It's a trick to solve some convergence problems in console. Maybe in another software there is no problem to use 0 here, but in console it's better to use 1. And of course, as the resistivity or the conductivity of the superconductor will be very, very high than 1, and so it's will be not a problem for us. Of course, this superconductor will have a critical electrical field equal to 1 microvolt per centimeter. It's a very, very common parameter that we use to model the critical electrical fields. We have here a critical current equal to 500, and the transition index equal to 25. And we apply here, it's a case to apply a current equal to 450 with a frequency, usual current with a frequency of 50. Okay? Here we have the mesh of this problem that we use it to mesh the superconductor domain on a paid mesh. Okay. And here we have the implementation, the border of the implementation in console. Here we have the resistivity and the source term that comes from the A formulation, and we apply this equation here in the global, as I show you in the last slides. We have the first results where we can see that the magnetic field and the current density show us the correct results as we expected for superconductor. It means that the current that is in superconducting have a correct form, as well the magnetic flux density. And for check if the integration, if the imposition of the current is correct, I integrate in another way this superconductor domain just to check if my imposition of the current is correct. And as we can see here, it's correct. Now, computing the same problem with the same characteristics, just right now imposing a magnetic field in a y direction, and let's see the induction, the computation of the induction of the currents in superconducting domain. We use here, of course, the Dirichlet boundary condition to impose the magnetic field in the boundary here. And so, as we can see here, the superconducting has a correct current density that we can see here. The current is inside of the plane and outside of the plane. It indicates a circulation of the currents to avoid the penetration of the magnetic field inside the superconductor. Of course, in this case, as this value of the magnetic field was so high, we induced and with the current penetrated a lot in the superconducting domain. Now, I would like just to emphasize the two publications that I could see in the literature about the JA formulation. It's the first publication that was done by me, by Barbara, Felipe, Flávio, Guilherme, and Professor Rubens, and a very nice publication as well, the numerical calculation of a high temperature superconductor with JA formulation that was developed by Silhan Wang et al. But it was also published in 2023. So, as a conclusion, this was here presented a new formulation, but this formulation has a high potential to accelerate the computation times, include considering ferromagnetic materials. There is open opportunities to implement MGB2 problems in JA formulation and also to contribute in the densified method approximation. I also would like to see some implementations in this field. As I told you, this formulation gives a possibility to implement superconducting ferromagnetic materials and so on. So I also would like to thank you again for Professor Frederick Bloom for this invitation. It, for me, was very, very pleasure to stay here. And I put in my contact if anyone would like to talk more about this implementation. Thank you so much. Thank you so much.
Thank you, Gabriel. Thank you very much. Now we have some space for some questions. So I see there is a hand in the teams, no? Edgar. Please, Edgar. Can you switch on your microphone, Edgar, or is there an issue on our side?
Yeah, I think that
it's good. Okay.
It was necessary to. Yeah. Thank you for the talk, Gabriel. It was really interesting for me that I'm familiar with these topics. Yeah, I have many questions, but most of them I will ask these questions after reading the references. But just briefly, in the slide number 8.
Slide number 8.
8. Yeah, I think that you have think about that and you have the answer. But if this is too long, maybe we can talk about later. But why you can neglect the electric potential in your second equation?
Yeah, it's a very nice equation. When I was designing this presentation, I was thinking if it would be better put it or not. But yeah, the grad of V, we could neglect if we are not coupling with electrical circuit. If we would like to coupling this formulation with the electrical circuits, we probably use the grad of V. But it's not necessary. Yeah, it's the fact. And Barbara and I are working in probably in the few months we will speak more about that because Barbara and I are working exactly in this topic and how to coupling the electrical circuit in JA formulation. That as we could to see if we use this, if we need to couple it with some external circuits, we need to use this grad of V, but it's not necessary. It's just that.
Okay. Maybe I was thinking that it is so small, orders of magnitude low, that not considering it, it's not a problem in the rest of the calculation?
I think that it's because the electrical field is all covered. Imagine that we have here some parts of the electrical field. Imagine a tape, for example. Yeah. If we have a resistance of the state and an inductance of the state, right? So both these terms are covered by these terms here.
Okay.
But if you would like to employ some external voltage, external source, we need to use this gravity to impose it.
Okay.
It's I could understand this equation, and I could see if, but of course this is a very new formulation, so we need to explore more.
Okay. Yeah, because at the end this looks very similar to the TA formulation, just that the order of the ordinary differential equation it's 1 and not 2. No? That's
this is the reason, because the JA formulation could to get less time to compute than the TA formulation, because it's a less order.
Sure. Yeah. And maybe in your slide 16.
16.
Yeah, the previous one, 15.
Sorry.
Yeah, this could be useful also to model stacks, like.
Exactly. Yeah, it's a good. Yeah.
Nice.
Of course.
Thank you for your answers.
Thank you for the question.
Yeah, I will read the information and then go back to.
Okay. And of course, if you want, contact me.
Yeah, nice.
Perfect. Thank you, Edgar. Actually, Gabriel, we have discussed this on the, and I will get back to what Edgar was talking about, because we discussed between us, no, on the potential, and the conclusion I had at the time was that this potential usually is referring to impressing the current inside a coil, for example. And in 2D, this is not necessary to put it, because actually you use a constraint in COMSOL to impress the transport current inside the coil. So that's why you can neglect this part. But I think in 3D, it cannot be neglected. That was my argument. I think in 3D, you need it. Is it true, this, or am I overstepping?
As I could see in the paper published by C1, it's not necessary. It's not necessary, but I will check. I will check and inform you. But as I could remember, it's not needed.
Okay. Thanks.
Thank you.
Okay, can I?
Yeah. Okay, Gal. Go ahead.
Yeah, just a comment, because I assume that I see that you are using COMSOL, but we always say that okay, this is possible to implement this in another tool. Have you tried, and just briefly, which is your experience about that?
Not yet, but Barbara and I are working to try to implement it in the GATP and specialize, but it's a very hard way.
Okay.
Professor Taylor could also talk more about the implementation in the GATP, but it's not very easy as in COMSOL. So, but we will try just to prove my phrase. But I believe that it's a very, very straightforward to implement.
Okay.
Yeah, I think in this case, if you want my opinion, as if in the homogeneous version it will be simple, but in the line approximation, that would not be easy for the constraint we have to apply, because we have to cut the air to apply the current there. So we will have to use the gradient of V in this case. You don't have a choice, because then you have to impose the current on a cut, on a thick cut in the mesh. That would be how to deal with it.
Thank you.
You're welcome. Other questions about this work, the JA formulations? Otras preguntas? No, I think this is the same, no? That's the leftover, no, Wilder? No, si quieren preguntar en español también, ¿no? No hay problema. Gabriel puede entender y puede responder también en español.
Sí, si no pasa nada, si quieres también preguntar en español, apuntar.
No parece que hay, ¿no? Wilder. No? I have another question then, Gabriel. There is something very interesting that you mentioned in your case study. You said in the air, the electrical conductivity is equal to 1.
Exactly.
So because air, usually you will think the electrical conductivity will be a lot larger than 1 Siemens per meter, no? Or 1 ohm meter, no? So why this choice? Why do you do that?
We need to use these conductance due to the form that console computes or creates the stiffness matrix. So if we use zero here, in some cases, not for our case, but in some cases, the way that console generates the mesh, we could get some very spurious between the very high conductance. If we have, for example, here superconductor domain, we have in this stiffness matrix a very high conductance or a very small resistance, and here a very small resistance equal to 0. So it creates a divergence in the problem of console. I believe that is just a trick needed in console, but in another problems it's going to be not a problem.
I see. And why 1? Have you tried other values?
Okay.
Because 1 is...
One, it was a common that as I could study in the superconducting fields, all of the authors that I could talk use 1, and so I just continue to use 1. But of course, if you'd like to use 0.1 or 0.0.0.001, I don't know. I don't explore how small could be the conductivity to activate the convergence without, or better speaking, what is the point that we got the divergence of the problem. I don't explore it.
Yeah, I think if you go too low, like 10 to the power minus 14, you are in the critical current of the superconductor, and then the current is spilling into the air, because actually you solve the H formulation in the air in this case. That means even with 1, you have some currents in the air actually. It spills out some currents that is completely negligible, but this is how it's done. And I never knew why they use 1. I think it was just numerical. It was just a value, random value that they use there. Thank you.
But I will check. I will check to inform you. I will check here and I will check what is the point that we got the divergence. I will inform you.
I see. I don't think Edgar wants to ask something new. Huh? I think it's a leftover, the hand. No, it's a leftover. I don't think...
Yeah, it's a leftover.
Yeah, it's a leftover. Okay, perfect. No, in case, no. I don't know if there are any other questions. No sé si hay otras preguntas o dudas en YouTube, en Facebook o en Teams. Huh? ¿No? ¿En la asistencia? ¿Alguien tiene alguna pregunta? Perfecto. Entonces, muchas gracias, Gabriel. Thank you very much for your time and for your talk. And you have a recognition. So I'm going to send you the recognition by email. And when I see you, I will give it to you. And a small token. A teacup as well. We'll try to give it whenever we can, no? So let's thank you again, the speaker, and see you soon then. Thank you very much.
See you soon. Bye-bye. Thank you. Thank you.
Thanks. So this is 11:45. At 12, we have our next talk. with Dr. Shiro Calzolaio. So we will wait a little bit, so we have a break, a longer break, but at 12 we start over with the last talk. A las 11 regresamos, hacemos una pausa. A las 12, perdón, regresamos, hacemos una pausa de 15 minutos y empezamos con la presentación del Dr. Shiro Calzolaio para concluir esta jornada sobre la superconductividad y sus aplicaciones. Nos vemos al ratito. Gracias. We see each other very soon at 12.
Camera.
Excellent. We can see it.
Microphone. But now.
You could
Okay,
share.
I just switch off from Firefox.
I can see the presentation projected on my side. So is it you, Shiro?
That's it. Oh, no, it's not that.
Shiro?
Yeah, can you hear me?
See, I can hear you, but I'm asking because I see on my side, I see your presentation shared on my screen.
But it's, well, it's not mine actually.
It's not yours.
It's my presentation, but it's not me sharing. Yeah.
Do we go ahead with your with this format?
I found it, yeah.
You found it? Okay.
Can you see my screen?
Yeah, I can see your screen.
Oh. It's a PDF, you see it?
I see myself actually on the screen.
Oh, why?
So you are, yes, this is something that should be there more. If you go to more or stop sharing, you need to share your presentation, or if you share your screen, you need to share the. So a few minutes more, trying to solve this little issue of sharing the presentation. Algunos minutos más, estamos tratando de resolver este problema. Oh, excellent. Thank you very much. Okay. So, yeah, that works. We can see it. Okay, so we can go ahead.
Now it's fine.
Perfect.
Sorry for the...
Oh, that's
sorry
fine.
for the delay and for the inconvenience. Yeah.
No, that's fine. Okay, as long as it's solved, it's perfect. So let's start with Dr. Shiro Calsolaio. So Dr. Shiro Calsolaio holds a PhD in physics in 2013 from École Polytechnique Fédérale de Lausanne, EPFL, Switzerland. He joined in 2015 the magnetic section of the Paul Scherrer Institute in Switzerland, where he has held the measurements and analysis group since 2020. His research interests include the design and construction of resistive and permanent magnets as well as superconducting magnets. In his area of interest, he is the author or co-author of more than 20 papers published in peer-reviewed journals or conference proceedings. Please, Dr. Shiro Calsolaio, the floor is yours. Thank you.
So, good morning, everybody. Thanks, Professor Theo, for the nice introduction. I'm going to give you an overview of actually some activities that are going on at Paul Scherrer Institute in Switzerland concerning the design of superconducting magnets for accelerator facilities. So at PSI, so this is just the outline of the presentation. I will focus basically on two main accelerators we have, which are the Swiss light source and the accelerators for proton therapy. And then I'm gonna discuss about design of superconducting magnets for these particular accelerators. So I will go through the magnetic design, thermal design, mechanical, and quench, and some general conclusions. So at PSI, we have actually quite a zoo of accelerators. So we have proton accelerators. Here you can see actually a very large cyclotron. Then we have a spallation neutron source, which uses actually the protons coming from this big cyclotron. And we also have a muon source. Then we have the so-called Swiss light source, which is a storage ring, which is actually today our main job because we are upgrading it. Then in terms of our electron accelerators, we have the Swiss light, we have the Swiss free electron laser. And then, last but not least, we have accelerators for proton therapy. as I told you already, today I'm going to discuss mainly about the Swiss light source and the proton therapy facilities. And in the course of the presentation, I'm going to switch between basically an example of superconducting magnet that we're going to install in the Swiss light source, and an example of superconducting magnet that we could in future install in the proton beam line. So I start with the upgrade of the Swiss light source. It's our accelerator for our electron accelerator at PSI. For this upgrade, we need basically to replace all the storage ring, and we needed to design and then to build and to measure basically more than 1,200 magnets, including basically resistive electromagnets, permanent magnets, and 2 superconducting magnets. Here just an overview about our Zeus magnets. So basically we have here on the top row here we have permanent magnets. So you can see an example of dipole. This is a combined function, dipole and quadrupole. This is a so-called superband, which is basically a dipole with a longitudinal gradient, which will be used in our storage ring to produce hard X-rays. A quadrupole made with permanent magnet, and then here you can see basically classical resistive magnets. A quadrupole, a sextupole, and this is an octupole by itself, but actually we use as a combined function octupole, quadrupole, and screw quadrupole. So here you can see a view of the inside of the building where we are gonna update and upgrade our machine. And actually at the 2 locations for 2 beam lines, the idea is to, basically during the first phase of the project, we are going to just install, let's say, room temperature magnet, both permanent and electromagnet. And then for the phase 2, at the 2 locations, we are going to remove this guy here, so this permanent magnet here, which is a super band, and we are going to install a superconducting magnet, so a superconducting super band, that has to be a cryogen-free or almost cryogen-free magnet, because we don't have really, or it was not convenient to build an infrastructure to have liquid helium and liquid nitrogen for the screen flowing all around the tunnel just for 2 magnets. So it's basically a magnet that relies on cryocoolers. And this will be used actually for the phase 2 of our project, but it's already in production, this magnet here. On the other side, as I told you already, I'm going to talk about the proton therapy. So just briefly, why proton therapy is important? Well, proton therapy is important because indeed it allows to spare healthy tissues when we irradiate the patient. Here on this plot, you can see basically the energy deposited by a proton, which is characterized by the Bragg peak. So actually the peak of the energy is located at a certain position, and this position is, you can calculate quite precisely this position. So you can spare the healthy tissues and you can deposit all your energy where you want. Whereas when you irradiate with electrons or with photons, with X-rays, actually the peak of the dose, it's actually at the surface of the patient himself or herself. Proton therapy has a lot of advantages, especially for in case of kids where surrounding tissues are more delicate and where actually the risk of secondary tumors is higher. And here you can see basically, well, it's the same concept of here. You can see that with the protons we are much more localized and we can really target the tumor. We have at PSI quite a long tradition in terms of proton therapy. So starting from 1980 with the Pyrotrain project, And then actually we had the first beam line dedicated to treatment of patients in 1984 with Optis, which is a fixed line, which is used to treat the high tumor. And then going ahead in the early 2000, we got the first, we got a dedicated superconducting cyclotron for the proton beam lines. And in the first decades of the 2000, we got basically our main machine, which is the Gantry 2, and we really developed this rescanning technique, which allows actually to, as when it was developed over the years, it allows really to scan the tumor and to deposit the energy exactly where you want, and in case also to repaint, so to redeposit energy if the required dose to kill the tumor is, I mean, exceeds certain thresholds. I want to point it out in terms of the pioneering project that we had, that already in 1980 there was this project that actually was not built, but it was still nice to conceive. Basically, it was a machine called the Pyotron, involving already superconducting coils. So here there was a set of superconducting coils based on iodine titanium to confine the pions, and then here basically was the bed with the patient. So we have here. This is just an overlook, just to see how many, so how the infrastructure is located at PSI. So here, this is Optis, which is the line for the eye tumor. Here is here we have basically the superconducting cyclotron, and then we have basically 3 gantries that indeed we use for patient treatment. Here a picture of the Gantry 2, which, as I told you, it's the most complex gantry we have at PSI, and it's a resistive magnet. In this case, it's a 2 Tesla dipole, and is quite a big beast. I mean, we had the idea of basically producing something like that, but using superconducting magnets in order to improve the performance of this machine. This is basically the sketch of what we proposed. So far, the project, I mean, we still have to find the financing for that, but we had a nice project, at least for conceptual design. And the idea was to make an Auburn-Fritin magnet capable of fast ramping, because you need to change the energy of the proton in order to change the penetration depth of the proton in the tumor. So if we move actually to the topic of this school, superconducting magnets, so well, superconducting magnet design, it's really a multiphysics problem. So of course, as you know very well, and actually you have to jungle between the magnetic, thermal, mechanical aspects, mechanical design. Of course, one constraint, or actually is, I mean, the first important point is actually the to see which superconductor can you use for a certain particular application. And here, for instance, the example of what we did for the, in this case, for the superband, so for the superconducting magnet for the Swiss light source. So depending on the performance of the magnet, so basically peak field at the, in this case, electron location, that then translates to a certain peak field at the conductor location, you can actually spot in this nice ensemble of superconductor where actually you can work. So at which material can you work? At the end, we went for quite well conservative option for the Swiss light source, and we are gonna build a magnet based on iodine titanium, because actually the operating range is in this region here. The specs of the magnets are here listed. So we needed actually, it's a dipole. This dipole has to produce a longitudinal gradient. So the electron has to see in its path an increasing field with a peak and then a decrease. The full wave F maximum of this profile has to be quite narrow. And what they need, what the beam physicists needed, it's actually tunability. So they needed the possibility to change the peak field of the dipole between basically almost 3 Tesla and 5.5 Tesla. Of course, the storage ring will stay the same when you change peak field, and so indeed the field integral has to stay constant. That was the constraint. But for all the scenarios, you see that actually the field enhancement, so the ratio between the B field at the conductor location divided the B field in the good field region, so the B field seen by the electron in this case, this ratio doesn't exceed 1.1, which is the case at 5 Tesla. So basically we were quite good to go with beam titanium. And okay, we selected the conduction cooling actually also to have the possibility to place the coils as close as possible to the beam. So if we go a bit deeper in the magnetic design, we stay with the super band. So with this example here, this is magnetically how does it look like. You have a set of basically two solenoids outside just to guarantee the field integral that you need, and then actually you have two racetrack inside to boost the field and to produce a peak like that. So here you can see basically the background field produced by the outer coils, the outer solenoids, and then here in blue you can see the field produced by the racetrack, which is actually the peak field that you need for the to produce Ardex rays in the storage rig. As I told you, the beam physicists told us that they require the tunability. So actually, you can change the current setting in the coils in order to have different peak fields by keeping this field integral always constant. And okay, this had some implication, especially for the thermal design, because of course to have the possibility to tune the current basically in the racetrack and in the solenoid, you need basically two power supplies, you need two sets of current leads, so you have a bit more thermal input. Challenges when we deal with magnets that have to stay in a storage ring is with other 1,000 magnets in the same ring. It's of course the crosstalk. So actually it was quite a big part of the magnetic design, the study of the leaking field or the stray field of this magnet. We were also studying a different configuration for this, so like an H-frame or a C-shaped magnet, and of course mechanical stability, because indeed we are very, I mean, at the end we are sensitive to mechanical errors. So if these forces would actually tilt the coils too much, you would introduce actually harmonic in your field, which are not which then you cannot correct in the storage ring, and so at the end the optic of your storage ring won't work. We did analysis to check the impact of the rho, yaw, and pitch angle on the magnetic field, because actually in the reality we will have alignment errors, which okay didn't show let's say we didn't have showstoppers in this phase here. Also, we analyzed the problem of misalignments of the coils, because again we had to deal with mechanical tolerances in a mechanical assembly. And also here, basically, by studying the harmonic contents, we saw that indeed we are not so sensitive to these coil misalignments. But the challenge is really in the suspension straps here, because if we have a small roll angle here, we are talking about basically 2 millirad, This 2 millirad translates in 20 units of A1. A1 means a skew dipole, so it's a dipole. So the normal dipole is going vertically in this direction. The skew dipole is orthogonal to that, and this is basically at the limit of what we can correct in the machine. So just to give you an idea about the tolerances that we have to achieve in the storage ring. As I told you, the crosstalk, it's actually it's an issue. So basically, when we decide, it's a challenge. When we design the magnet, every magnet, also the resistive and the permanent magnet, we cannot design the magnet one by one as a standalone magnet. We have basically to check the impact of the neighboring magnets. So in this case, you can see a magnetic model of the superconducting superband, including also the cryostat walls. And here is actually a permanent magnet, which is a combined function dipole and quadrupole. So this is the profile of the B1, so the dipole components along the beam path, and the B2, so the quadrupole components along the B path. So just to say, in this particular case of the storage ring, the crosstalk, it's an issue, and whenever you design a magnet, you need to take into account also the neighboring magnets. Was the same actually also for the gantry machine. So as I already told you, I'm gonna switch from one application to the other. So these problems of mechanical tolerances and crosstalk were exactly the same we had in the gantry application, because indeed the dipole that I showed you was meant to be installed in a beamline like that. And the idea was to have the possibility to shoot protons in this beamline and to focus the proton at the patient, which is located here. In this cartoon here, you see basically a beam with a momentum deviation of 7%, because actually plus minus 7%, because indeed the idea was actually to have the possibility to shoot protons at different energy in order to make also this repainting in depth, so to have the possibility to scan the tumor also in depth. And the alignment of the magnets is to be so precise, because at the end, well, you have to focus the beam, also if the beam has different energies. And well, it's very easy to make mistakes here. So if you just, in this case, I just shifted this quadrupole. It was in the range of 0.4 millimeters, and well, you can see that actually the reference particle, which was traveling at with an energy which was the nominal one plus 7% in terms of momentum, was just completely off. So okay, this was just going in another direction. So here we developed actually an iterative procedure in order to align the magnets, and we had to go in the range of 0.1 millimeters. I mean, here the scale, I don't know if you can see, but it's in meters, so these are quite large magnets. So, and we developed basically an iterative procedure, first to align the dipoles. So here we, you see the errors, so the displacement, how we had to displace the magnets, just to align first the dipoles, and then actually we were turning on the quadrupoles to check also basically the focusing effect on the beam. When we have the coil, so the magnets for the gantry have also another challenge, which is related to the AC losses, basically. So these magnets have to be, they don't work in steady state. As I told you, you need to have the possibility to shoot the protons at different energy, actually to scan the tumor in depth, and the penetration depth, of course, is proportional to the energy of the beam. So from one side, the optic is made such that you can transport a beam with different energies without changing the setting of the magnet. But if you exceed basically this number, which is plus minus 7% in terms of momentum, then the optic is not, let's say, good enough in order to transport this beam. And so you need to change the field of your magnets, and you have to be quick to change the field, because from the other side of the magnet the patient is waiting, and so actually the treatment itself cannot last long. Also because sometimes we have moving tumors, because the patients of course have to breathe, and of course there is the heartbeat. The tumors are not really static objects, so you have to change the field quickly. And so there is all the problem of designing a magnet in order to minimize the AC losses. So here you can see basically the AC losses calculations in the structure. So here, for instance, in the support structure, including the yoke, these were the copper strips that we were using for the cooling. With several options, because we had to cut the strips in order to minimize the eddy currents, and even in the thermal shield, of course, you induce currents, and then you have to dissipate this power. But of course, not only in the support structure, so to say, but also in the superconductor itself, you have different losses. So you have hysteresis losses, because indeed the magnetization of a superconductor is not linear with the field. So this is a typical magnetization cycle. So you have hysteresis losses. And then you have, if you look inside, so if you have a cable, you have interstrand losses. So because the current, when you ramp up the field, up and down, the current is gonna flow basically between the strands. Inside the single strands, then the current is also going to flow among the filaments, and so you have also interfilaments coupling losses. So it's really a multi-scale problem, and you have to go from the losses in the big structures, the big support structure, to basically the interfilament losses inside the superconductor. All this then, of course, will have an impact in the thermal design. We start, as before, with the superconducting superband. In this case, the magnet is indeed steady-state magnet. So the problem of the AC losses here is really minimized, because indeed you have to change field just when you turn on the magnet, and you can ramp very smoothly the current. Here you can see basically a schematics of the superband. It relies on two cryocoolers for redundancy, basically. The machine has to work with a reliability which is almost it's 99.999%. So, and if the superband fails, you have to shut down the whole storage ring. So that's actually not acceptable, or actually we have to minimize this risk. In our previous design, we also had an helium reservoir with the idea of using the cryocoolers as recondensing units. And this was actually also to get a better contact between the 4.2 Kelvin surface and the yoke. And then basically the coils that are located here are cooled by conduction. Of course, the challenge here was the design of the copper straps, so the thermal path between the cryocooler and the coils. Basically, with we are going to use two stages cryocoolers. Because we need to cool down the shield, because there is a thermal shield here which has to stay at 50-60 Kelvin, and then we have to cool down the cold mass, which has to stay at 4 Kelvin, basically. With our design, basically, we can also cool down the magnet by pumping, also by pouring actually a liquid helium in this reservoir, or actually directly by conduction, thanks to the cryocoolers, which otherwise work as a recondensing unit. The thermal balance was indeed quite an important task, because we had to be sure that actually all the losses that we have in the magnet, from the splices, the suspension straps, the radiation losses, HTS lead, all this source of heat actually has to be counterbalanced by the power of the cryocooler. And of course, if you look, this is actually the heat capacity of the cryocooler. So it tells you actually the power that the cryocooler can absorb. Our operating point is here. This means that actually the cryocooler at 4 Kelvin can absorb something in the range of 1.5 watts. So you can imagine that it's not a huge amount of power. And considering also that the heat capacity of the material at that temperature is pretty low, you may very quickly basically quench the magnet. So you may very quickly overcome basically the current sharing temperature of your strands. Quite an effort. We put quite an effort to design actually the thermomechanical structure around the coil. So we needed basically a structure here to pre-compress the coils. And the point was also to try to use this structure as a heat path, so to say, so to really have an homogeneous temperature distribution in the coils. So here you can see basically the aluminum ring which goes around the outer coil, so the outer solenoid, and then this is the support structure of the racetrack inside. And also, the challenge was to minimize the heat gradient in the shield and in the suspension straps. So these are basically the suspension straps which go from the cold mass to the cryostat. And so basically from here you have basically 300 Kelvin, and then here you have to stay at 4 Kelvin. So you have to minimize the heat load coming from the suspension strap. And the main point here was actually to clamp the middle point of the suspension straps to the screen, to the thermal screen around, just to intercept most of the heat coming from the 300 Kelvin environment. If we switch back to the gantry, so in the thermal design, the additional challenge with respect to the super bond, so of course a lot of problems were the same, so minimizing heat load coming from the straps, the radiation from the screen and so on. But in the gantry, the additional challenge was actually the AC, the fact that we have to work in AC. And so if you just write the heat balance equation, you will see that here you have a lot of terms, which are the eddy current, which are hysteresis losses, interfilament losses, interstrand losses in the leads, and the Joule heating that, of course, you you might have if you overcome your TCS in the coils, and you have in any case from the resistive part of the leads. So here you can see actually the profile of the field versus time. So actually this tells you how we meant to sweep the field in time. And this is basically the calculated, this is actually the black one is the calculated current sharing temperature of the coil. And this was the red one, was the maximum delta T in the, or the maximum temperature actually in the coil. So the main problem here was really to minimize all this source of heat, because as you can see in this summary plot here on the right, so the coil has its own enthalpy, so you have an enthalpy margin, which is actually the enthalpy at the TCS, so at the current sharing temperature, minus the enthalpy of the cold mass at the operating temperature. This is, the black one is the energy that the cryocooler can absorb, and the blue one here is actually the energy which corresponds to AC losses. So it's the AC losses power integrated in time. And actually, if you are too fast in the cycles, or if you repeat these cycles too many times, you can see that at a certain point, actually, the cryocooler cannot recover all this power, and so at the end, you might be in trouble. So the temperature of your magnet can increase. So this was actually the additional challenge of the gantry magnet, because again, you had to take into account all these dynamic effects, and all depends actually upon the speed of this field sweep. And the field of this sweep actually was not decided by us, but it's an input that comes from the medical physicist that have to analyze how fast you need to sweep the field in order to treat the tumor. So how fast you need to scan the tumor in depth. If we go to the mechanical design now, so as I mentioned you before, the thermal structure was also, so we try to use the mechanical structure also to distribute the heat in the coils. So the support structure of the super band relies on pre-compression rings. For the outer solenoid, it's okay. It's pretty simple. It's really a compression ring. For the inner racetrack, there is actually an aluminum ring which presses some compression pads, and then the pads is compressing the racetrack coil. This because the racetrack has a shape which was not really. So a ring would have compressed also the top part here of the coil, which is actually where pre-compression is not required. For this reason, we went for this option with the pad, which is actually tailored on the shape of the racetrack. And here we did some simplified test in liquid nitrogen, where indeed we didn't use the pad, we just used an aluminum piece, but it was machined such that we could leave a gap here at the edge in order to like mimic this big aperture that we have here in the calculation. Here's some results, which depends upon the pre-compression that you give at the beginning. So basically the aluminum ring was supposed to be mounted with an interference. So the idea was actually to warm up the aluminum ring and then to slide the aluminum ring around the coil. And the goal of this exercise was actually to see which configuration could minimize the deformation of the coil, especially between these two scenarios. So just after cool down without Lorentz forces, and then after powering with the Lorentz forces, of course. The other point was actually to consider the full structure around the coils. So, for instance, well, we have to screw actually the pads, and so it was important to consider basically the friction between the screws and the supports. So the friction had to be also minimized, because in any case you want these pads to move when the aluminum ring around shrinks. And so, well, you don't want to lose much pre-compression as a consequence of this friction here. All these problems are highly nonlinear, because you have to design the contacts between the various parts of the support structure. And in this particular case, I was using again COMSOL to make this actually this multi-physics coupling between the magnetic design and the mechanical design. Okay, for the external coil, the concept is the same, but is actually easier because we just need an aluminum ring to pre-compress the inner coil. I mean, for solenoids, it's indeed usually much more easy, the design of the mechanical structure. So here you can see basically the same kind of calculation, but I mean, it's just something to counteract the up stress action. When we go, so the super band is niobium, so it's made in with niobium titanium. So niobium titanium is not strain sensitive. For the gantry, the additional so for the gantry magnet, the additional challenge was okay, AC losses, as we said before, but actually we wanted to use niobium 13. Because with niobium titanium we didn't have enough margin. HDS was back to the time was too expensive, and so we didn't select HDS. So niobium 13 was the conductor of choice. So that the additional challenge is that actually niobium 13 is brittle, and on top of that is strain sensitive. So you have to make an effort also to minimize the deformation, and you don't want to crack your strand inside the cable. For this magnet, we plan to use Rutherford cables. So here it's a simplified cross-section. Also was a small Rutherford cable made of 12 strands. And this is actually the stress-strain curve of one single strand. And this is actually the curve that we use for the mechanical calculation to estimate the strain and then the stress inside the cable. Also here, it was a multi-scale approach, starting from an homogenized model of the coil, going through still an homogenized model of a cable inside the coil, to go actually to a twist pitch of the Rutherford cable inside the coil. The idea here was really to calculate the strain inside the strands, and then actually when you know the strain inside the strands, actually you can, using the behavior of JC against the strain, you can actually estimate where you land here, and so you can estimate your quench margin basically. Indeed, with the multi-scale approach, you can go also further, because so if you take basically, if you select the strand where you have the peak stress, then you can go deeper into the analysis, and you can see actually what happened in the strand itself among the superconducting filaments. So this is basically the strands. Okay, this was the non-deformed configuration. Then you can see actually the real strain, or in this case was a stress distribution in the superconductor, in this case niobium-13 filaments. Quench, so well, we said it's a multi-physics problem, and quench indeed is a multi-physics problem. The quench protection for both the superband and the gantry magnet is a classical one. It relies on an external dump resistor. So whenever we overcome a certain voltage threshold, and we overcome this threshold for longer than a certain validation time, we need to dump the energy of the magnet into an external dump resistor. So this sort of schematic circuit is basically valid for both the gantry and the superband. Of course, then in the detail we have differences and so on, but so to say the main idea is the same. So for the superband, of course, we started with, let's say, analytical calculation, Mike's calculation, just to see basically the quench margin we have, both in terms of well, current, so quench margin, and in terms of temperature. So here you can see basically the number for the outer coils, so the solenoids, and for the inner coils, the racetrack. It was very helpful to produce this sort of maps. So this basically was the damping constant of the outer coils and the damping constant of the inner coils, taking into account, of course, the inductive coupling between these two sets of coils. Because once you have this map, you can basically see in which region you want to stay, and you can select basically the damp resistor you need. The point was, of course, to have an hotspot temperature not that high, but also on the other side, you don't want to have more than 1 kilovolt of voltage, because then it becomes more cumbersome, the insulation. So this was the trade-off: minimizing the hotspot temperature, but also the voltage for both the outer and the inner coil. We did some 3D simulation, because in this simulation here, in these maps, these were very, it was a very nice tool, but of course it was basically an analytical calculation. Indeed, then we checked with, again, a COMSOL model, a 3D model, where we could also plug into the model basically the AC losses, because now, when you dump the current, of course, you have then a dB in dt, which produces AC losses. We needed to estimate the role of the interfilament coupling losses, and to see how the quench develop in the magnet. I have here actually a small video. I don't know if you can see it. Which shows you the evolution of the quench. So the idea was to start to trigger a quench in the inner coil, and then you can see that as a function of the as a consequence actually of the currents induced in all the structure in the magnets, after a few milliseconds you quench also the other coils. So here, just for the sake of the clarity, I plotted the outer coils far apart, but I mean, of course, the coils are concentric here. But basically the point is you start quenching the inner coil, and then you induce currents, eddy currents a bit everywhere during the discharge, and you quench the full magnet. But okay, the good point was that actually the hotspot temperature was not going more than 100 Kelvin or so. So we feel safe from this point. Another very nice thing I want to mention is actually in the frame of this superconducting magnet of the superband is a nice collaboration I have with Professor Trio, who is actually so for all the model I was showing you, I was using COMSOL, whereas with Frederic Triad, and Frederic is also developing all these tools in Elmer in this case, to simulate all the different aspects that we require for the design of the superband using open source alternatives. And so, yeah, this is, I'm showing you some of the plots that actually Frederic showed when he came in our institute last year. So wanted just to stress this nice job by Frederic and this nice collaboration we have to see to look for open source alternative to the COMSOL or our commercial softwares. If we we talk about quench. As I said, for the gantry magnet, it's the same principle. So we have an external dump resistor, but there is a caveat. The gantry magnet, as I told you already, is niobium-13, so it's brittle and strain sensitive. Therefore, when you do also this quench, you have to also to take care about how the stress in the coil evolves. And here you can see basically the evolution of the stress in the coil during the quench discharge and during the evolution of the temperature. Just a few words about the future project at PSI, and then I'm done. So we are trying to develop also the infrastructure in the frame of this chart, which is actually an ensemble of Swiss labs dealing with superconductivity, applied superconductivity. So we are developing, and we will build basically quite a large lab to build the magnet. We have developed also a lab where we can magnetically characterize the magnets. So here you can see actually room temperature magnets. But then we have also a test stand where we can test at the moment small cryogen-free magnets using cryocoolers. And another project that we are working on is about actually a shield, a superconducting shield. In this case, we want to use a high-temperature superconductor, and this is in the frame of an experiment that we want to perform at PSI to look for the electron dipole moment of the muons. So the idea would be to have a solenoid where you let spiraling your muons, but the physicists need here basically an injection channel at the zero field. So you have to screen the fringe field coming from the solenoid. In this case, again with COMSOL, I was using this AH coupling to simulate the shield, and yes, to see basically to estimate the screening factor that we might have with different configuration of shield. One of these was the shield made with tapes, YBCO tapes, and one, which is actually the most promising, is the case with YBCO bulks, so an array of bulks. And okay, so this project is in an early stage, but I mean we try to go ahead with that as well. So I hope I could give you an overview about some projects that we have at PSI. We have at PSI the challenge, but also the big chance actually to deal with different accelerators. And for these accelerators, we deal with basically permanent magnets, room temperature electromagnets, and superconducting magnets. And, well, of course, as you know, the design of a magnet is, in particular if it's a superconducting magnet, is really a multi-physics problems, which makes the things really interesting in my eye. And with that, I'm done. Thanks for your attention.
Thank you very much, Shiro. Thank you for this nice talk. We will see if there are any questions from the audience and online. I don't know if someone, yes, from the audience, please.
Well, very interesting presentation. Could you explain in more specific terms what are the advantages of using the racetrack coil inside the solenoid? I saw that you use that in order to get higher magnetic fields, but
yes,
there are other advantages.
Well, yes. So basically, you mean this one, right?
Yes.
Yeah. So basically, if you just use the solenoids here, you will have a bell shape field. So we need to use this magnet to produce hard X-rays. So the thinner is the field profile here. So the higher is the bending radius seen by the electrons, the higher is the energy of these X-rays. We need to produce hard X-rays, so we need actually an abrupt change of trajectory for the electrons. For this reason, what we need to do is actually to boost the field in the middle in order to have this profile, this peculiar profile. With a bell-shaped profile, at the end of the day, what you do is you reduce the emittance of your machine at the end. So that was the main issue. And so this was the reason why we need to focus and to concentrate the flux lines with racetracks to boost the field really in the middle. Otherwise, you end up with a bell-shaped magnet. So profile, sorry.
Okay, you play with
it was a requirement for the production of X-rays, indeed.
Okay, you are playing with the inductance. I see.
Well, it's not inductance. We are playing with the at the end with the extraction of I mean, here the electrons when they see a bending field, when they see a dipole field, they bend, of course, and during the bending they produce a synchrotron radiation, and the energy of this synchrotron radiation is basically proportional to this bending radius. So the bending radius produced by the field. And so for us, it was an input, actually, the field profile, because we needed to match a certain energy of the X-rays that is required for the experiments.
Okay, thanks. Thanks for your answer.
Thank you. Any other questions? Online? Yes. So, Gabriel, please.
Firstly, congratulations for your presentation, Ciro. It's a very nice presentation. I'm very interested in the A approach and A multi-scale approach that you showed us in the next slide. I don't remember the number.
The mechanical one, in the mechanical model, you mean?
I believe that's the mechanical model. But the first question is, this one, this name A is not about the A formulation, no? It's,
no, this is a multi-scale approach. No, sorry, it's just, no. A formulation, I was using.
It's the first one, but before the stupid question, I would like to know how you could or what was the boundary conditions that you used to employ or to study for the bulk and looking into your problem. If I could understand, firstly, you simulate the figure A, and after somehow you implement some boundary conditions in figure B, and so on at the figure E, A, C, D, E. Yeah, exactly, the figure E.
Yeah, okay, yes, this. So, yeah. Mm-hmm.
How do you simulate, or how do you create these boundary conditions? Because it's a very interest for me. And I believe that it's going to be implemented in another problem, for example, in magnetic fields, and it's a very nice idea.
No, absolutely, yes. This approach is used, well, for instance, in mechanics is very much used, because actually sometimes you have stresses in structures, but indeed these structures have substructures that you cannot take into account in a global model, because indeed you don't have enough calculation power and so on. So here the point was, I was calculating. Okay, in this case with the A formulation, if you indeed with the A formulation, I was calculating the field in this coil, which was just homogenized, so nothing special. And then I was, in any case, the mechanical properties of these coils were, I mean, I had a tensor to simulate the mechanical properties of this homogenized coil. So I started already taking into account the structure of the coil in the homogenized model. With this, I could basically spot where do we have problems, so to say. So here we had this red spot. So here we have the concentration of stress somehow. After that, what I could do is actually I could refine the region where we had the highest stresses. Actually, I just refined the region, and this region here, it's indeed corresponds to the volume occupied by a cable. After that, so, and this, if you want, is made in the main model. So it was basically first a model of the homogenized winding pack. Then I was refining, but in the main model, so to say, I was refining this region here, because here was the region where we spotted some problem. And so after that, I was calculating the displacement in this tiny region here, which corresponds basically to 2 twist pitch of the racetrack cable. And in the sub model here, I was importing the displacement. In these models here, I could not. No, of course, here you don't have any friction. Basically, this one, it's a pure elastic model. This one instead, where we input actually the displacement coming from this submodel, we could actually here use, because of course the scale now of the problem is smaller, we could use actually the elastoplastic behavior of the strand. So I had some measurements of the elastoplastic behavior. So this was a stress strain curve that I measured at 4.2 Kelvin. And so I could basically plug into this model the stress strain of the niobium free thin strand, and I could also basically simulate the contact between the strand. So you have also basically the friction between the strands. And this, I have to be honest, was already enough to evaluate the margin you have. This was up to here was enough. But then, of course, you can go further. Because with this approach, you can go down in scale. So once you have the displacement in this model, of course, you can apply this displacement to a zoom in the strand. But I have to be honest, for the design of the magnet, basically these 3 steps were enough. Because at the end of the day, you have the JC versus strain and versus field measured on the full strand. So this one was really to go into the structure of the strands to see if, by collaborating with the company producing the strand, if we could actually improve something in the architecture of the strands. But so to say, I don't think that this step here is necessary for the magnet design. If you rely on a strand that you buy, if you are also developing the strand itself, well, it's another approach. And for instance, CERN is doing that. And indeed, I was doing that when I was collaborating with CERN, because CERN they need also to boost the research in the conductor itself, so to say.
Perfect.
But this was a bit the process, and here it was the displacement, actually, the if you want the coupling between the homogenized model and the detailed model, which is elastoplastic.
Okay, perfect. Thank you for your answer. Is there some publication about that I could read?
Yeah, we are working on that with Frederic, actually. We should have,
Okay, yeah.
We have been working on this for years now.
Okay. So I'm waiting. Thank you.
Thank you.
Is there any other questions for Dr. Shiro? No, online, no. In the audience, someone has a question? I have a question, Shiro. Your background is in physics, and
I'm a nuclear engineering actually as background, and then just the PhD was in physics. Yeah.
Okay, because this is interesting in this kind of work that we find different profiles. No, we find people from engineering, people from physics, people from materials, and along our career, we deal with different people. No, and we all do the same thing. In particular, for the design of magnets for superconductivity, actually, is where we merge those different profiles to solve the technological problems that are very advanced, we can say, but this is interesting because it's something that in Mexico we haven't seen, no? Profile that can go from physics to engineering and the way around. So not something that has been very often seen, but in CERN, for example, it's something very common. Do you agree on this? That's the question. Do you agree on this? And what is your opinion regarding this aspect? No.
No, absolutely. As I also concluded this presentation, so it's really a multi-physics problem. When you deal with magnets in general, and in particular with superconducting magnets, it's indeed you have to deal indeed with multi-physics or multi-aspects. I don't know how to call them problems. And so indeed you must you cannot rely only on the classical magnetic design. I mean, because of course, well, you have all other physics which are coupled to that. So. It's another challenge because you need to have a broad spectrum of interaction, so to say. So either a broad spectrum of know-how or a broad spectrum of interaction with other people, as you said, in order to dig into these problems. Because at the end, of course, it's difficult to, so to say, to focus all this in one person, of course. So it's very good to have multi-physics problems because you get chance to collaborate with a lot of different people, a lot of different profiles. Yeah, absolutely.
Thank you, Shiro. I think we can conclude, and I can hear behind you the baby crying with the mother. I'm not mistaken, no? I'm not mistaken.
No. Yeah, they disagree maybe on the multi-scale approach here.
Yeah, multi-scale, multitasking approach here. So enjoy. I think, look, Shiro, I have, like I said with Gabriel, I have a document to send you. So I will scan this document to acknowledge your participation. Thanks. I have a gift for you, and when I see you in Europe, I will bring it with me. And
Thanks a lot.
Thank you. And we can thank again the speaker and the speakers as well as we finish. Yes, go ahead, Shiro.
And thank you for the opportunity, actually.
Thank you.
Thanks for inviting me and for giving me this opportunity to show our work.
Yeah, no, thanks very much to participate. So I would like to thank the audience. I would like to thank the participation online and all the speakers for their contribution and their time. And this school is not finished. There is another set of presentations next week in the Institute of Physics of the UNAM. And you can attend. This is presential. This will be also transmitted online. But it will be nice to see people attending live this event. So we wait for you next week in the Institute of Physics. I'm going to switch to Spanish. Entonces, muchas gracias a todos. Muchas gracias a los que atendieron esta escuela hoy. Si empezaron en Puebla, nos siguen, ¿no? Todavía. Y yo quiero agradecer a los ponentes de hoy que hicieron un buen trabajo por su tiempo. Y a todos que participaron, y yo recuerdo que la próxima semana sigue la Escuela de Superconductividad en el Instituto de Física. Entonces es un evento presencial también, entonces si pueden atender de manera presencial estará perfecto, si no pueden también en línea atender este evento. Esperamos que aprovecharon de este evento y que si están interesando en trabajar con nosotros o con los colegas que trabajan alrededor de la superconductividad, las puertas están abiertas y buen día, buena noche para algunos y nos vemos pronto. Gracias a todos. Muchas gracias. Chao, chao. Hasta luego. Concluimos. Bye, bye.
Gracias a todos.
Chao.
Ciao.